sort of wanted to give for a long time. It's kind of a mix of all the research we've done on BGP over the last 6 years. And so what I'm going to be talking about is the challenges of securing the internet's routing protocol. This is a problem that when I started my PhD in 2006-5 was already considered like we've been working on this for too long and we can't solve these problems. People were kind of throwing up their hands. And what my research has been about for the last few years is trying to understand why is it for this protocol. What properties do you actually get from these security protocols, and how do you actually get them deployed? So when I say what properties do you actually get, so most people in this room, I suppose, know what a digital signature is, right? So cryptographic digital signature. So basically, a lot of these protocols are doing things like taking messages and digitally signing them, okay, which sounds like a good thing to do. But then the question is, what does that actually do in terms of the properties of the network as a whole? So you have an interconnected network with lots of different systems talking to each other, and if some of the messages are cryptographically signed, what does that actually mean in terms of preventing attacks? Okay, so that's what we're going to be spending most of the time on. I'm going to start by talking about the actual security issues with BGP. Then I'm going to talk about the two major proposed solutions right now for securing BGP, actually three. One of them is called the RPKI, the Resource Public Key Infrastructure, that is currently being deployed. One of them people have probably heard of, which I think as of today is still not standardized. I don't think the RFC number is out yet for that protocol. And then something called prefix filtering, which has been used widely since 20 years ago. Okay, so I'm going to talk about all these different security protocols and how they actually affect internet routing. Okay, so also, if you want to ask me questions, please just stop and put up your hand if you want to ask me questions, and Hebrew I will understand you and answer you. So, it's kind of fun. Okay, so, all right, so we're going to start by just reviewing how BGP works. So BGP is used to set up routes between autonomous systems. And so the view of the internet we're going to be using for the rest of this lecture is the AS level internet. So at the AS level internet, what we have is giant networks. And we're going to think of each one of these networks as a node. So for example, the Technion has a network. That network has a single AS number. I don't know what it is. I can tell you the Boston University's AS number is 111. Okay, so these are networks and they have numbers. Princeton has an AS, that's AS 88. Okay, so for small networks, what we consider small at the BGP level, like a university, a company, right? Each one of those is generally has an autonomous system. So what I'm showing you here is different ASs. This is NTT. This is actually a very large network. These are some smaller networks. This is a small network in the Netherlands. This is the network that hosts spam house servers. So what I'm going to show you is, first I'm going to show you how routing works, and then we're going to talk about an attack that actually happened a couple of years ago. Okay, so first of all, so BGP is used to learn routes to IP prefixes. Okay, so this is a server. It has a host name, and it has an IP address. Okay, so this is the things we're sort of generally familiar with. If we were to do routing at the level of computing a route to each individual IP address, we would have 2 to the 32 routes. That would be too many routes. Okay, it's too big. So what we do is we instead compute routes to what's called IP prefixes, which is blocks of IP addresses. This here is an IP prefix, 204.16.254.0/24. Okay, so what does this mean? It means all the IP addresses that have this prefix. Okay, so /24 means the first 24 bits are common, which means these bits, and these bits are common. Okay, so this IP address here, 204.16.254.40, is a subset of this /24 IP prefix. It's a single address inside here. So this IP prefix contains all addresses from 204.16.254.0 all the way up to 204.16.254.255. Okay, because there's 2 to the 8 addresses inside the /24. Why is it 8? 32 minus 8. 32 bits for an IP address. First 24 bits are common. You have 8 bits left over. Okay, questions on this? Okay, so this is actually important. IP prefixes are going to be relevant to this talk, but we'll see more about them later. Okay, so here we have this IP prefix that contains the IP address that is of this server. So now, if we wanted to reach this IP prefix, what happens is that this autonomous system here, which is a large network, a large hosting network, is going to advertise that it is the holder of this IP prefix. Okay, so what this here is a BGP message that says if you would like to reach this IP prefix, which I'm showing here, this IP prefix, I am the network that holds it, 2997. Okay, and then this route gets propagated around to its neighbors, and this network SCNet is going to choose this route. So I'm showing that it's selected this route to here, and then it's going to announce itself on the path as well. So BGP is what's called a path vector protocol, which means that each network just puts its name on the path. So you can see here, as the path propagates through the network, the BGP announcement made by this autonomous system is its own AS number, the one before it and the one before it. So each one just appends their name onto the path, and that's how routing with BGP works. Okay. All right. Okay. So you can see that finally when this network here, green hosts, learned the route to this IP prefix, it's got a path of length 4, NTT, NLayer, SCNet, and AS2997, and this is the route it's going to select. It's a 4-hop long route, and this is how it gets this IP prefix. I just want to emphasize that these nodes that you're seeing here, these clouds, these are not individual routers. There could be many, many, many routers and devices inside each one of these networks. This is just what we consider like an organization or a single logical point in this network, okay, because we're routing in between networks. BGP means the border gateway protocol, so the idea is to route between different networks. Okay, is that good? I'm not sure of the level of people in the room, so please stop me if I'm over or under your head. Okay, so how many people remember this attack from 2013? There was a huge DDoS attack, and all the newspapers wrote it was the biggest DDoS attack of the internet, 300 gigabits per second. You remember this? So this was, and a lot of this was publicized by Cloudflare, which has a reason to publicize this because they prevent DDoS attacks. Anyway, so this was in all the newspapers. Now, what's interesting, including the New York Times, and this is interesting because it's like 1 or 2 months before the Snowden revelation. So this was still at the time where you wouldn't really see technology stuff in the papers in the US. So, so this attack was all over the papers. But what I found sort of interesting about this attack is at the time it was one of the first cases where we knew that a BGP attack had happened on purpose, maliciously. Okay, this is in 2013. And so let me show you what happened. This is Cyberbunker. This is what's called a bulletproof hosting provider. So basically it provides hosting, and if there's abuse messages or whatever it is, they sort of ignore it. Okay, so this is what it's thought to be, Cyberbunker. So there was an announcement made by Cyberbunker that was the following. They sent out this BGP message into this link here was actually inside an internet exchange point in the Netherlands. Okay, so they sent out this routing message here, and they said that this IP prefix 204.16.254.40/32 can be reached through this path of different ASs, 34109, 51787, and 1198. So 34109 is Cyberbunker, and these are some other systems, autonomous systems. Interestingly, when I made these slides several years ago, these autonomous systems were no longer online. Okay, so these could have been very short-lived autonomous systems, or like something that came and went, something very sketchy. Okay, let's say that. Okay, so how many IP addresses are inside this IP address block, the /32? 1. Okay, good. So so we have here a /32, and we have here a /24. I'm sure even if you don't work in routing, you've probably heard the term longest prefix match routing. Okay, the longest prefix match routing or most specific prefix match routing. Okay, so longest prefix match routing is the way we do routing in the internet with IP. So what happens is when you get an IP packet and it has an IP address on it, you have to decide where to send it. Okay, so what you do is you have routes to different IP prefixes in your routing table, and you find the IP prefix that matches most closely. Okay, so what happened in this case was Greenhost had 2 routes. Okay. One route to 204.16.254.0/24, and one to this one here, which is a /32. Okay, so let's say I have a packet that's destined for this server here. Okay, which route am I going to select? Am I going to select the route to the /32 or the route to the /24? /32, because it's the longer prefix and it matches, right? Longest prefix match routing. So even though this is a matching prefix, this one's longer, so it's preferable. Okay. So what ended up happening was packets that were destined to to this spam house server here this guy, actually ended up going here to Cyberbunker, because what he did was he announced this route that caused the networks that learned this, that selected this route, to install a route in their routing table for this /32, which is more specific and therefore is always preferred. Okay, does that make sense? Okay, so now did Cyberbunker actually own this prefix? No. Do they have any business announcing this prefix? No, they should not have announced this. And in fact, they even claimed that they did this. So the attacker, this is from Twitter, much worse than 30 gigabit DOS, Cyberbunker, BGP Hijack, spam house IPs. So that's BGP Hijack is what I'm showing you right here. This was their BGP Hijack, and this was the attacker stop house actually says, yeah, we did this. Okay, so it's actually funny what they did. What they did was, yes. Nothing. They were just, so what they were trying to do was they were upset that Spam House is a service that blacklists IP addresses, and their IP addresses were blacklisted, these attackers, so they wanted to retaliate. So their retaliation was to hit them with a lot of packets. That was the DDoS attack, and the other thing that they did was hijack their IPs. And in this particular example, what I'm showing you, what they did was, the way that Spam House works is that server that I showed you here. So if you're like a routing geek, this is sort of interesting. Do you see that this is 0.ns? What is this? It's a DNS name server, right? This is a DNS name server. If you don't know what I'm talking about, don't worry. This is a DNS name server. So the way that Spam House worked was that you sent DNS queries to this server for the IP address that you wanted to know if it was blacklisted or not. And then I think it would tell you the IP address was localhost 127.0.0 if it was spam, and something else if it wasn't. And so they were using basically the domain name system to answer these questions. So what these guys did was they set up their own server that for every IP, if you asked if it was blacklisted, they responded yes. So every query you sent, was this blacklisted? They just said yes to everything. Okay, so that was this particular attack. So the reason I show this is because I can sort of walk through all of the different protocols that I want to walk through in this talk, and also because at the time when I made these slides, this was the first time that we'd seen cases where attackers were taking credit for something like this. Okay, so in a second, I'm going to talk about why, you know, in 2013, it was the first time we saw people actually taking credit for these types of attacks. Any more questions about this? Okay. Okay, so this type of stuff has been happening for years. This is in 2010, a report to Congress. Maybe you've heard about this, that the China hijacks a huge fraction of the US's IP prefixes. Okay, so here's what actually happened here. In 2010, there was a case where China Telecom announced to the internet 15% of the internet's IP prefixes, and in the way that they announced them was what's called a prefix hijack. So what I just showed you here, this is called a sub-prefix hijack. Why sub-prefix hijack? This prefix, that's the hijacking one, is a subset of this prefix, right? /32 is a sub-prefix of the /24. Makes sense? Okay, so sub-prefix hijacks are really bad. Why? Because basically the sub-prefix is always going to be preferred regardless. It doesn't matter if the path is really long, right? It doesn't matter. As long as this route for the sub-prefix exists in your routing table, it will always be selected. Okay? You can see here in this case, actually, the attacker's doing well because the path you can see here is 4 hops long, and the paths you can see here is 3. So actually, the real route is longer than the attack route, so that's better for the attacker. But you could imagine a case where the attack route was really, really long. It wouldn't matter, right? Because the sub-prefix is the most important thing. Does that make sense? So in this case, of this China Telecom case that made a lot of news in the US, it was a prefix hijack. So if my prefix was something something /24, the hijacker was announcing something something /24 as well. Okay, so that means that if the attack prefix was going to be selected, they had to have a more attractive route, and we'll learn about what that means later. It's not like what we just saw, sub-prefix hijacks, where you win all the time. So the outcome of this was basically a lot of speculation was whether or not this was an attack, and the reason that we still don't know, whether or not this was a malicious attack or just a mistake, we still don't know. The reason is because a prefix hijack is something that actually happens by mistake a lot. So for example, in 2006, Con Ed, which is a power company in the US, did like exactly the same thing that this China Telecom did in 2010 that made all the newspapers. It was exactly the same type of incident. This incident here that happened in 2014 was Indosat hijacking also a massive number of the internet's IP prefixes. Again, it was a mistake. So a lot of times these things happen by mistake. This case here, do people remember this? The Pakistan YouTube prefix hijack. This was another thing that made a lot of news. What ended up happening was that Pakistan took YouTube offline for 2 hours by hijacking their IP prefixes. The type of incident that this was a sub-prefix hijacks, just like what I showed you on the previous slide. We actually know why this happened. This happened because Pakistan was trying to censor YouTube, and the way they did it, they kind of screwed up the way they did it, and they ended up censoring it for the whole internet rather than just inside Pakistan. So they were trying to announce, you know, their hijacked prefixes into Pakistan only, and they left Pakistan, went out into the whole internet, and sort of hijacked all the internet's traffic to Pakistan. Okay, so, and we actually have a copy of the Pakistani Telecommunications Authority, like, order to censor these prefixes, and that's why this happened. So that was, you know, up until 2013, and then we start to see more sketchy-looking things. This was another thing that made the news in the U.S. There was a hijack from a source in Denver, Colorado, to a destination in Denver, Colorado, that went all the way through Iceland, London, and then back. And there was actually sort of marks in the BGP announcements that showed that this was done deliberately. Yeah. Oh, yeah. That's the whole point. Yes, sorry, I should have made that point. Thank you for... We will see how we're working towards doing that, but at the moment, no. There is no pinning of certain routes. So all of these incidents are like networks, like either just being like, oh, I own the whole internet. Actually, in 1997, there was a very, very famous incident where they realized that, like, oh my God, BGP is not secure, where one network announced the entire internet and black holed the whole internet. This was like a long time ago when there wasn't that much internet traffic, so it wasn't like as horrible it would have been as today. This stuff rarely happens today, like that level of horribleness. But that's sort of what started this whole thing. And then over the years, what we're seeing is from these really large scale, like I'm going to announce 15% of the internet's prefixes, like this China thing I showed you, to I'm going to pick a very specific prefix and very carefully manipulate the routes. This is what this thing is, so that I can get the traffic to go through me and then come back. Okay? So basically, these are two kinds of incidents. This is what we call an interception. So what happened here was the traffic kind of like left Denver and went all the way to Iceland and came back. They were able to do this because they were very careful about how they selected their routes. There are other attacks in which you kind of, or incidents in which you kind of announce the whole internet to the internet. They all think you are the internet and all the traffic goes to you. You become a sinkhole for the traffic and there's nowhere for the traffic to go because your neighbors all think that you are the destination. So the traffic can't leave you. Does that make sense? So those black hole attacks are what I was showing you before. And these are these more specific targeted incidents. This one is another targeted incident here, where someone hijacked the IPs of Bitcoin miners in order to draw the traffic to their own servers so they could manipulate the way they were mining Bitcoin. So this is in 2014 where we are starting to see more like malicious or deliberate incidents. And this is in, last year. Last year, it was revealed that the Italian police was working with hacking team to do BGP hijacks to get back into IPs that they lost access to. Yeah. I've never heard of anything like that before. You should tell me what let me look into it. I don't know. I've not heard of trading scams specifically using this vector before. There were some incidents where they know that IPs of banks were hijacked, but I've never seen an investigation that showed that there was actual malicious stuff happening at application layer. What's interesting about this is that you can see the hijacks inside BGP, but then trying to figure out like what application they were targeting is really hard. So, for example, this thing with this was revealed because of emails in Italian that an Italian internet researcher read and figured this out, and then they went and looked in the BGP announcements and saw that this was true. The hacking team incident. This Bitcoin thing, I believe, was revealed because they actually found that the Bitcoins were stolen, and then they tried to figure out how it was done, and they realized it was BGP. But it's more often that when you monitor BGP, you see strange things, and you have no idea why they're happening, because maybe there's some application, and who knows which one, that was being targeted for a few minutes, and then it was You know, so it's all very hazy about why this stuff tends to happen. More questions? All right. Okay, so as was pointed out by the person in the corner, BGP doesn't really have a pinning of routes to holders of IP prefixes. Anyone can kind of go and say whatever they want. And so this sounds like something we could fix with crypto. And one of the current solutions is called the Resource Public Key Infrastructure, the RPKI. Okay, so what this thing is doing is something that seems pretty obvious. What we've been seeing in all my slides so far is autonomous systems announcing IP prefixes that don't belong to them, right? So what is the RPKI doing? It's making a mapping between autonomous systems and the IP prefixes that belong to them. Simple, okay? So it's a cryptographically signed certificate hierarchy saying which prefixes belong to which organizations. This was standardized in 2012. It's covering about 5% or 6% of the internet's IP prefixes right now. So deployment has been very slow. And one of the things I'm going to talk about is why it's been so slow in the second half of my talk. Okay, so what's amazing and wonderful about the RPKI that we're going to see is it actually solves a lot of problems, and it doesn't actually require any changes to BGP. Okay, so we're going to see exactly how it works in a second, but it's something running on top of BGP. It's not actually going and changing BGP full scale. Now, BGP Sec is something that was first started to develop in 1997. And what BGP Sec is a full replacement of BGP. Okay, so what it's doing is instead of using BGP in the same message format that we've had for all these years, it's changing the message format. It's requiring cryptographically signed BGP messages, and it's requiring that every BGP message be validated. Okay, so you can imagine a protocol that exchanges a lot of messages, and now you have to do crypto on each message. For cryptographers in the room, this is public key crypto. This is not symmetric key crypto. This is not fast crypto. These are RSA or ECDSA digital signatures that are being applied to the message. And for every network on the path, you need a cryptographic signature. So I'm going to show you exactly how this protocol works, but this is like serious crypto. And so this is a big deal because it's a big change to the system, and it requires upgrading routers with crypto accelerators and things like this. Okay, so I'm happy to talk about all the different crypto issues of deploying secure BGP. But this was, back in the day, they kind of tried to do both of these pieces together, and then they realized maybe we should separate them out and do this first and then this second. And that's why we have RPKI and BGP Sec. If you remember secure BGP from 20 years ago, it was basically these two ideas stuck together. Okay, so again, I'm not really sure of the background of people in the room. Have people heard of IPv6? Yes? So how long have we been deploying IPv6? 20 years? Okay. So I think if you kind of keep track of what we've been doing, you know, I've heard of DNSSEC. I'll speak a little bit about DNSSEC. How long have we been deploying DNSSEC? Okay, like 10 years, let's say. So all these protocols, they take a really, really, really long time to deploy. And I think BGP is particularly prone to these issues. IPv6 is even worse, but actually BGP has a lot of the similar issues. What is the challenge? We have a working internet. We can't just go and like throw it away and build a new internet and just magically have all the protocols we want to be cryptographically secure. We have to actually deploy them and not break the internet at the same time. So the incremental deployment challenge and ensuring backwards compatibility with today's internet is a huge challenge as we try to secure these protocols, and that's going to come out in this talk. So if you wanted to design a secure BGP, you could probably do it, like my undergrads can do it in their homeworks, but actually getting this deployed is where the real sort of technical challenges and deployment challenges lie. So that's what we're mostly going to be focused on. Is there any questions about this? If you don't quite understand what these two systems work, how these work, I'm going to go into great detail on how they work all through the talk. Okay. All right. Okay, so these are two papers that we wrote on this topic. What we're going to do is we're going to try to understand what sort of security benefits you get with a system like the RPKI, where the important thing to remember is it's not a full-scale replacement of BGP, as compared to something like BGP Sec, which is really a replacement or a new protocol that runs on top of BGP. RPKI is something that can kind of run out of band, whereas BGP Sec is something that requires a complete change to the BGP message structure and the upgrade to routers. So we're trying to understand when you go from this technology to this technology, obviously this one is more secure, right? And we'll see why. but this is more secure, but what are you getting as you make this transition? How much more security benefits are you actually getting? So we're going to look at how we measure that. The spoiler is RPKI is really important, and the change from RPKI to BGP Sec is less than we might expect, and I'm going to talk about why that is. And then the second thing I'm going to talk about is RPKI itself. So when we see the RPKI, it may look, I don't know, depending on your background, you may look at it and think this thing is totally trivial, and why haven't we deployed it already? Or you may look at it and think this is horrifying, it's never going to work. So I'm going to talk about some of the issues about deploying RPKI and how it affects the security of the system. Okay, so those are the sort of two parts of it. Good. Okay, so let's start with RPKI. I'm going to just, this is the part of the talk where we're going to look at all these protocols and see how they work. And then we'll talk about the actual deployment. And then we're going to see what sort of they bring to the network. So if you deploy RPKI versus BGP Sec, what you actually get in terms of preventing the attacks that we've looked at. All right, so what is the RPKI? So the RPKI is a certificate hierarchy. So it's completely out of band. This is the logical view of the RPKI. I'll show you the actual implementation of it later. But what it's doing is it's a hierarchy of certificates. And so what I'm showing you here is the American Registry of Internet Numbers. This is the authority that allocates IP prefixes to organizations in the US, Canada, and the Caribbean. So I think Israel is part of RIPE. Does anyone know? Right? So, yeah. So there are 5 of these, what's called regional internet registries, RIRs. This is the US one, and then there's others, 4 others. These ones each one allocates some subset of the IP address space to organizations. So in this picture, I'm showing an allocation of a /12 IP prefix to Sprint. So how many IP addresses in a /12? It's 2 to the 20 IP addresses. Okay, so this is big. The /12 is the big. Big enough. We have a /16 at BU, which to me is huge. So Boston University has actually, I think, almost 2 /16s, which is enormous. And the reason we have 2 is because we got them in the 80s or 90s, or early 90s. MIT has a /8 to themselves. So that's really big. So this IP prefix belonged to Sprint. They've sub-allocated it to other organizations. So what I'm showing here, you can see this /20 is a subset of the /12. And this /24 is a subset of this /12, and these are different organizations. So what the RPKI would do, it would give certificates to the holders of IP prefixes in a hierarchy. So you can see that in order to have, if this prefix, in order for this certificate to be valid, all of the certificates above it must contain the IP prefix in this one. So this IP prefix is contained in here, and Aaron is containing this IP prefix. Okay? And so this is sort of just a certificate hierarchy allocating prefixes. These are cryptographically signed. They're just digital certificates, just the standard like what you have in SSL or in the internet generally. This is just X509 certificates. And now the special object that's issued in the RPKI is called a ROA. That stands for Route Origin Authorization, I think. Authorization. And what it is it's a mapping between an IP prefix and an autonomous system. Okay, so in this, this ROA is a /4/32 that is held by this autonomous system here. Okay, so you can see this ROA here is for the /24, which is a subset of this IP prefix, which is a subset of that IP prefix, and you can see that there's subsets all the way up. Okay, so these ROAs are the objects that protect you from routing attacks, and in a second we're going to see how. Okay, so as I said, this is an out-of-band system. It's just, you build the certificate hierarchy, and then it exists, and you use it to check the correctness of routing. Any questions on that? All right, so let's see how this actually helps. So imagine that we had a ROA for this IP prefix. So this was the IP prefix that was attacked here by cyberfucker. If we had a ROA that said that AS2997 is the holder of this IP prefix, then if we had a ROA, and if Greenhost was actually validating the routes, then he would be able to see that this BGP announcement is valid. Why? Because the origin, what we call the origin AS, the first hop, matches the one in the ROA, right? And meanwhile, here, this is invalid. Why? Because we don't have a ROA that matches this thing. Make sense? Okay? And so now, Greenhost knows that this route is not valid. It won't put this in its routing table, and therefore the correct route will be added to the routing table, and he will select the correct route. Okay, so that's basically what the RPKI is doing. Yeah. Yes. Yes. So RPKI doesn't prevent that attack, and we're going to see it. I think you're going to see it. Yes. Okay. So you jumped ahead of me. I want to take more questions on this, and then I want to talk about how you jumped ahead of me. Okay. Just notice, though, what is awesome about this system. Because everybody does what you just did. Everybody looks at this and like, but there's another attack. Okay, before we look at the next attack, which everybody should think of how you would still attack this system if you could, I want to point out something. That now, you cannot get away with announcing subprefixes. You can't do this anymore. Because if you want to announce a subprefix, there better be a ROA for it. Okay? So, for example, there would be no ROA for this /32. Because nobody wants to go around announcing the /32. Let me say that again. This is really important. This /32 prefix will not have a ROA in the RPKI. It should not have a ROA. Okay? Nobody's going around announcing a /32. Even though this IP address exists, right? We saw it was the server that's here that I made disappear. This ROA would never exist in this system because this network never announces this block of addresses as /32s. It only announces the /24s. So getting away with this sort of announcement is just not going to happen. You won't be able to do a /32. You'll have to do a /24. Does it make sense? Okay, this is important. So again, as I said before, longest prefix match routing, if you can exploit that as an attacker, that's great, because that means your routes always win. It doesn't matter, right? Longest prefix match routing will always pick your routes. But now that we have the RPKI, these things don't work. You can't have a ROA for this /32 prefix because nobody's actually announcing it in BGP. There would be no ROA for it in the system. And so this route will always be invalid. It doesn't matter what you stick over here in the path. The fact that you're announcing a /32 is just not going to happen. Yeah. Yeah, you're right. Okay. So let me tell you what the envisioned use of the system is. So the way that the system will work that I can show you later in more detail is that what you would do is you would have like what's called a prefix list in the router that would compare the routes against the prefix list and see if the route has if this prefix is not in its prefix list, it'll ignore it. Okay, so now this isn't a change to the actual BGP message structure. The BGP packets haven't changed at all. What you've done is you've pushed a module to routers that allows them to validate the correctness of routes. Okay, now routers already have modules that do this. Validating the correctness of routes against rules that the operator puts in manually is already done today. But we haven't changed the packet structure. Okay, so later I'm going to talk about how these rules actually get to the router and so on, but what's important to remember is what actually really happens in the system is that this thing that I showed you here, right? These are all cryptographic certificates and they require crypto and all that fun stuff, right? There's crypto here. The thing is though, that you can just validate this, right? And then get the result, just the list of ROAs that you have, and this is actually what they do. They get like a text list of prefix and AS, and they send that text list to the router via TLS or something, okay? So the router's not doing any crypto, it's some kind of server inside your network that's doing all this work, validating all this stuff, and then getting a list and sending it to you. So as I said, this is not a change to BGP, it's a change to sort of like the access control list that you're using to validate routes. It's not the actual message structure that's changing. Okay. More questions? Okay, so now, so we saw why this stops subprefix hijacks, because there will be no ROA for the subprefix if it's not supposed to be announced. Okay, great. So let's say you want to do an attack. How do you attack? What's the attack that you could still do on this system? Next level, right? So what is our attacker going to do? We call this the one-hop hijack. If our attacker was smart, then what he would do is he would say, well, you know, if I want to hijack that address, that .40 address, then what I've got to do is I've got to make sure that the first hop and the IP prefix match the one in the ROA. And so here we go. these match, right? I think I have a nice animation here. This is a valid announcement according to the RPKI, but the attacker's route is still preferred. Okay, so the attacker will succeed at the hijack here, right? Notice that this is not anymore a subprefix. This is the same prefix. Okay, so does it make sense why this attack is successful here? Sorry? It's not a route. So this is wrong because this link doesn't exist. He's lying. He's claiming that he's connected to the legitimate origin. He's claiming that he's connected. And so this guy will say, what should I do? I have two routes. One of them is 4 hops long, and the other one is 2 hops long. Which one should I choose? I'm going to choose the short one. Okay. So he wins. Make sense? So yes, it's still attackable. RPKI is still attackable. So exactly the instinct that you had, and that I'm sure several people in the audience had, is the reason that people kind of were like, okay, we can't leave it at the RPKI is not sufficient. There's a way to circumvent this, and that is true. But I want you to notice one thing. How did the attacker win here? He won because his path was shorter, right? Okay, so in order to win, he has to make sure his path is always shorter. Okay, so actually that starts to become hard because his path will be shorter for the people he's close to, but for people that he's far from, his path is no longer shorter. So the Pakistan YouTube incident is a great example, okay? That was a sub-prefix hijack. The hijacked prefix was a /22, and the hijacker announced a /24. Okay, so this hijacker announced a /24, which is a longer prefix. So that was preferred. So everybody went to Pakistan from everywhere, all over the place. It didn't matter how close you were to Pakistan Telecom. In something like this, yes, the attacker is doing better because he is closer to Greenhost. But let's say for this guy here, is this guy going to prefer the route through Cyberbunker? No, right? He has no reason to. He's much closer. Whereas if this was a /32 that made its way all the way out, then yes, this guy would turn himself around and go this way to Cyberbunker. Does that make sense? Because the /32, the more specific prefix is the most important consideration. You always match on prefix, and after that you select on routes. Okay? Questions on that? Okay, so yes, RPKI is easily circumvented by using this one hop hijack. But again, you are only going to win as the attacker when you're close to the people you're attacking. If you're far from them, if he wanted to attack SCNet, get SCNet to route through him, that would have been a lot more difficult because he's far away. Okay. Yeah. Your success is smaller, exactly. Yeah, and that's what we're going to see. Yeah, so if you're Akamai and you do hijacks, then you're in good shape, right? So if you're Akamai and you start hijacking from Akamai, all of Akamai's routers all over the world, Akamai is very, very connected and you're going to do well. But it might be a little harder to hijack out of all of Akamai's servers. So that's true. So what's happening here is I'm sort of spoiling my whole talk here, but I wanted to point this out as I'm going. It's what's happening is before, when you do the subprefix hijack, it's like any Joe Schmo who can announce a subprefix and get it out into the internet. He's doing really well. He's attacked everyone, okay? Whereas now, when we impose this constraint that you can only announce prefixes that actually match, and not only that they match, but you also have to claim you're connected to this guy, the real guy, which means you're forced to have one extra hop, right? Then you can win, but you still have to be close to people. So if you're Google or Akamai or Microsoft, then okay, good. But if you're Malaysia Telecom, you're going to be less effective than you would have been if you were sub-prefix hijacking. Okay, or Pakistan Telecom. More questions on this? Yes. With a sub-prefix hijack. Yes. With a prefix hijack, you would have a harder time because you need to be closer. Okay, so in Pakistan, yes. Sure, yeah, in Pakistan, sure. But then your impact is localized to Pakistan as opposed to the whole internet. Yeah. More questions? Okay. Okay, so again, to point out here, what was the decision point for Greenhost? How does he make his decision about where to route? He looks at the length of the route and he selects in that way. Okay. All right, so that's the RPKI, and that's why Pgp Sec is introduced. Yes. Yes. Yeah, no, that's true. I don't want to get into it now. We actually wrote about that. I would say that, honestly, I'm not satisfied with the answer that the system has right now. There's some efforts to improve it, but let's talk about that later. They actually were suggesting you just do rsync. Do you know rsync? It was rsync connections. Anyway, that's like a different topic. So the question was, like if you're trying to reach the server that serves these certificates, the RPKI certificates and the ROAs, and you're like offline because of a BGP attack, how are you going to reach those certificates? So that's a good question, and I don't believe that the system has completely solved that problem, actually. But that is an important question. Did you have a question there? No? Okay. Anything else? Okay. All right, so this is where we stand with the RPKI, and this has been standardized for, I guess, 5 years now, and is currently being deployed. I don't know if any, I think there's one organization in Israel, I think, that has a certificate, but not very widely deployed, and we'll talk about that shortly. Okay, so we saw this problem. What was the attack here? You announced a link that doesn't exist in the network, right? Okay, so what are you going to do? Introduce crypto, right? So we're going to introduce BGP Sec, which is cryptographically signed routing announcements. So in this picture, I'm going to color with orange the networks that have deployed BGP Sec. Okay? So what happens with BGP Sec? Now the RPKI not only creates ROAs for people, it also creates, not only does it certify ROAs for people, it now also certifies public keys. Okay, so each one of these autonomous systems is going to have a cryptographic public key. So I don't know how many people here are cryptographers, but this is exactly what you would do if you were a cryptographer. You would give each one of these systems a public key, and you would ask them to sign the announcement. And so this is what the announcement will look like. The announcement is, I am this AS. I hold this prefix, okay? And SCNet, I'm telling you that this is the path that I have, and this whole blob is signed by this key. All right? So when I draw this thing in yellow, I'm meaning that this entire message is signed. So the path SCNet 2997 and the prefix is signed by this network with the yellow key and sent in the BGP announcement, BGP Sec announcement. Okay, and then the next guy is going to sign the path himself. So he's signing to end layer that the path is SCNet 2997 and the prefix with his green key. And then he's including the previous guy's signature as well. Okay? And you can kind of guess how this goes on, and so on. Okay, so each guy announces the path that he has and signs it with his own key. Does this make sense? All right, so since we have time, why do we need each person's signature here? Would this be secure if we just had one signature? So what happens if the message structure was just without the yellow, just the green? Right, would that offer us any security against the attack that I showed you before? Yeah. Yeah, so if we didn't have this path here, right? You could just sign whatever you want. You could make up routes and just sign them because it's your key and you can just sign whatever you want. It's your key. So if we didn't include everyone's signature, then anyone could say whatever they wanted. So it's really important that we have everyone's signature there, so I can't just go around saying, like, here's my route, signed by me. Trust me. Because exactly the attack we saw before, if you'll see here, is he just announced whatever he felt like announcing, which wasn't true. Right? He claimed he had a route to this guy. He could have a key and sign this in BGP Sec and it would be fine, right? That wouldn't give us any security at all. Everyone's signature has to be there. Okay? And also, sometimes people wonder why you're signing up here. Why is this name in here? Right? So again, this name in here is really crucial because the whole reason that we prevent the attack we saw before is because in order to make his malicious announcement, he would need a message signed by the yellow key that says 3419, here's my route, I'm 2997, and this is the prefix. So in order to make his malicious attack that we saw before, he needs to actually have this message from the other guy, right, with his name in it. Okay, so you're signing the links of the path rather than the nodes of the path, basically. Okay? And so the fact that there's no way that Cyberbunker would have such an announcement because he's not actually connected to 2997 is the reason that this attack is prevented by BGP Sec. Okay? Makes sense? Okay, so why is this a fun protocol? Well, first of all, we are doing this with public key crypto. Why? Because, there's 50,000 autonomous systems, and they're all going to need keys. And so it's not going to happen that we're going to have symmetric keys between everyone, because then you'd have to, onion sign something a million times, 50,000 times. It's not going to work. Okay, so this is really public key crypto. You're doing public key crypto in the routers. Okay. This is also interesting because traditionally when we do public key crypto, like in SSL, typically there's only one key, like me and the server I'm talking to. In this protocol, there's just tons and tons of keys. If you're sitting there in your router validating announcements, you're going to need to have the keys of everybody and then use them to validate all the announcements that you get from everywhere. Okay, so this protocol is quite expensive because not only is it public key crypto, it's also lots and lots of keys. Think about SSL, the way you connect to a website securely. You connect to Google, you get Google's key, you do stuff, and then you have a symmetric key and you do crypto between yourselves. One key only. This protocol has many, many keys. Yeah. Yeah. Yeah, no, it's not high. It's not a super high rate. No, so when people think about the performance of this protocol, the question that you're always asking exactly sort of like the first thing, which is the first thing you think is how frequently are these messages coming? And the answer is not frequently. Okay, but when does this protocol become expensive? It actually, when we evaluated the performance of this protocol, we evaluated in one specific case, which is reboot. Okay, so when the router boots up, he comes up and he says, "Tell me all your routes," to his neighbors, and they start sending him routes. And so if you can think about it, even today when a router boots up with no BGP security, it takes it a while. It has to get all the routing announcements from its neighbors, read them all, put them in its table, do stuff. It takes time, it takes minutes. Okay, like 1, 2, 3 minutes. Now if you throw crypto on top of all of this, when it boots up, it's going to get all these announcements, it's going to have to validate them, and then potentially sign the routes that he selected and send them out to his neighbors. Okay? So in those cases, it's going to be slow. And so that's when you evaluate it. You evaluate at the moment where he turns on and he has to validate all the routes, install them in his routing table, and then make announcements to everyone else. And that's when it gets expensive. Like in the normal course of operation, it's not horrific in the way that you would think. This is not packet level. This is not nanoseconds. This is seconds or minutes or stuff like this. Okay? Yes. Yes. Sorry, it's in parallel. Yes. So BGP Sec has always been envisioned as the step 2 of RPKI. So first you need RPKI. Also, notice that BGP Sec does not. So if you look at this path, what are we certifying here? We're certifying the links. You're certifying that. So in this announcement, the red, right? NTT is NLayer is saying to NTT, there's a link between us and whatever I got from everyone else. That's what that red message says. The link between NTT and NLayer. The green message is certifying the link between SCNet and NLayer. Okay. The yellow message is certifying the link between 2997 and SCNet. Notice that I haven't certified the link between the prefix and the AS. Why? Because that happens in the RPKI. Okay, so the RPKI is certifying the mapping between prefix and autonomous system. Our BGP Sec is certifying the links between them. And then you need keys, and the keys will go inside the certificate infrastructure as well. Yeah. Yeah. Yeah, that's true. Yeah. Yeah. So yeah, this is an online signing system. So for example, I'll talk tomorrow about DNSSEC. So DNSSEC, one of the goals of DNSSEC was to not have the secret keys used for signing DNS to be sitting on the servers that are facing the internet. Now, routers for BGP would have to hold the secret keys, right? Because you saw this is a protocol that's happening and you get the message and you have to sign it and tell people, right? So you have to have your key because you have to sign it. It's adaptive. The whole reason the BGP Sec is designed in the way that it is so that you can adaptively sign based on what route you select. Okay. So yes, the keys have to be sitting in the routers. Okay. So I just want to say though that one thing about BGP routers that makes it better for them, and the reason that we don't have BGP hijacks like crazy all the time, is it's really hard to get access to a router. Like I cannot wake up one morning and say I'm going to log into like NTT's router and start, doing stuff. It's much more difficult to kind of get into these devices. Getting into something like the DNS is actually a lot easier because you have the vector of sending queries and caching and all this stuff that you can use. There's fabulous paper that's coming out at IMC about dynamic updates for DNS that just lets you like actually just tell the server like, hey, here's a record for you, and the server's like, great, and it accepts it. So there's none of this craziness in BGP. Like, you have to be in the router. So unless your routers are really like insecure, like password Cisco or something, like it's really hard to get into the router. So, you know, to do these types of attacks, you got to be Cyberbunker who has an AS that got into a system. You know, like you have to actually have an AS in order to do this. And that's why it's not the kind of attack you see people doing outside from their basement. Whereas things like DNS attacks are actually a lot easier to do because there's a lot more ways to get into the system than you can with routing. So that's, I think, one of the reasons that we're like, it's not as horrible as you might think. Yep. No, these are, yeah. No, that's a good idea. Yeah. Yeah, no, I agree with you. I actually don't know how they've started tackling these performance issues, but those are exactly the kind of thoughts that you need in order to get through the BGP Sec security performance issues. I haven't, the last year or two, seen what the story is in terms of how they plan to tackle these issues. One problem, I think, is that routers are always engineered like right up to their limit, and I'm not 100% sure why. They're always, you know, like very, very little CPU available. They're sort of engineered right up to the limit. So there's not a lot of CPU to be doing this, but maybe things are changing. I don't know. But that is the challenge. You're sort of trying to figure out how do you circumvent this issue. But yeah, that is the big issue. Okay. Yes. Mm-hmm. Yeah, so if you have a multi-homed organization, like, actually that's not the correct use of multi-homing. So what we mean here is a prefix that's announced by two ASs, yes. Okay, so the RPKI totally accommodates that, it's no problem at all. So we're going to get more into the RPKI later. The RPKI is a whitelist. I'm trying to see if there's an example even in this picture. Okay, there's not, but you can see that in this particular prefix it goes to several ASs. But you can even have a ROA for the same prefix and two different ASs. So the RPKI is intended to be a whitelist, which it lists the ASs and prefixes that are allowed to announce something. So you can have multiple prefix ASs that announce the same prefix. That's not a problem. Okay, it's not like a one-to-one. It's what you're looking for is a match. Okay, so if two ASs announce the same prefix, they each have ROAs, and those both routes will be valid. Okay. More questions? Yep. In BGP? Create denial of service by stale entries or old. Are you saying replay attacks? Are you saying replay attacks of BGP? Mm-hmm. Yeah. Yeah. So you know what? I actually lost track of how they prevent replays in BGP Sec. There was one way that I remember which was called beaconing. And what beaconing does is that the origin AS, this announcement here, would include its time. And so you wouldn't be able to, but the thing is, it's not that everyone would include their time, it's only this guy that would include their time. So if something was stale, if everyone was being honest, right, you wouldn't be able to, like, if these two guys were being honest, you wouldn't be able to replay this stale message. I guess if you could replay a stale message over here, I guess. You would, or you could kind of like manipulate the upper parts of the message, but I'm not sure where the timestamps go, which is bad because I'm like into time now, but I stopped paying attention to timestamps on this protocol because there was some back and forth on how to solve. Huh? Yeah. Yeah. Yeah, I guess you could do that, but the scope of such an attack would be limited to the link that you're doing the attack on. Okay, so if I was sending you junk, basically, to overload your CPU, I would potentially overload your CPU, but I wouldn't overload the whole internet's CPUs. Okay, so that's a big, big gain over something like a sub-prefix hijack where I send you some garbage and you propagate it and it goes to the whole internet and everybody is now routing to Pakistan instead of to YouTube, right? So we're looking at a smaller scope of an attack. There have been studies about DDoS attacks. Not DDoS. DDoS is the wrong word for BGP. DOS attacks on BGP that were exploiting like router bugs and stuff like that. But these are really like link-specific attacks rather than global attacks, which is what I'm focusing on here. Yeah. More questions? Okay. All right, so that's BGP Sec. And I think we've talked about sort of the challenges of BGP Sec quite a lot. But that's just the flavor of the engineering challenges that are coming with BGP Sec. Now, this is actually happening, by the way. So this is being standardized, and people are building implementations and stuff like that. So it's yet to be seen where this thing goes. Okay, so now we should talk a little bit about more background, how ASs choose route. Yes? Okay, so I'm 100% going to talk about that a lot, but later, the second part of the talk. So actually, the whole second part of the talk is about what is the trust model for this system, and do we really want to trust it? So exactly what you're asking me, when you start to have certificates, you start to think, like if you've thought about TLS a little bit, and what about the trust model for TLS, and like there are similar questions here. They're actually answered in a very different way, but it's a very important issue. So I want to focus on like routing and global properties right now, and then we'll talk about that stuff later. Okay, more background. So you've heard of longest prefix matched routing. You've probably heard of shortest path routing, right? We do that everywhere. However, no, we don't do that in BGP, actually. BGP is not a shortest path routing protocol. What's interesting about BGP is that each network makes its own routing decisions according to whatever it wants, officially. So when you say autonomous system in BGP, you mean autonomous system. They can make their own routing decisions. So what I'm showing you here is a very, very shortened version of the BGP decision process in routers. Yes. 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 Okay. To the whole route, actually, to the whole route. Yes. Yes. Okay. So let's look at, you know what? Let's look at this picture here, okay? So when I was kind of like going through this part, I was cheating a little bit, right? I was like, okay, here are two paths that this guy has to choose from. And I was like, okay, well, he's going to choose the shorter one. So I was cheating because I assumed you were going to assume that shortest routing is what we do in BGP, and we sort of do that. But we could, you know, technically, this network can make whatever decision he wants. So for example, he could have a routing policy that says, if I see SCNet in the path, don't use this route. Okay? There are some policies like of this form, like let's say you want to avoid a network that's known to censor certain types of packets, like you probably don't want to select routes through that network, right? So people can have routing policies like that. That's all fine. Yeah, you see that this is the message that he sees. Like this is the packet format. He sees this message, and he can make whatever decision to select whatever route he wants. He's got two routes to the /24, and he has to select one of them. And the criteria that he uses to select this route is whatever he wants. So in this picture, I showed it being shortest paths, but it could be, I don't like this network in the path. Or more commonly, it could be, how much does it cost for me to send traffic on this link? Okay. Sorry? Right. So yeah. So technically, from the like standards perspective, the standards does not standardize what your routing policy is. So like a phrase you often hear in the standards is it's a matter of local policy to blah 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 blah. Okay. So it's a matter of local policy to select your own routes in the way that you want. So everyone can select the routes in any way they want. Okay. Technically, from the standards perspective, you don't have to like do anything particular to be standards compliant. You can drop all paths that go through Asia if you want. You know, just because. It's up to you. It's your route. It's your system. You can do whatever you want. The thing is, though, that like, you know, these are routers, and they typically have this sort of like de facto process that happens, which is what they call the BGP decision process. And I'm really simplifying things, but there's this thing called local preference. Now, local preference is the knob that allows you to kind of do whatever you want. So local preference allows you to make decisions on whatever you want. Now, the most common type of routing policy that we have And I'm saying this because of an actual research paper that came out last year that showed, I think, 60 or 70% of routes of networks do this. And this was a paper at NDSS by Dave Chofness and Philippa Gill and several others. And if you're interested, I can send you the reference after. The most commonly used local preference is actually adheres to this model called the Gao-Rexford model, after Lishan Gao and Jennifer Rexford. I know Jenna has spoken here about some of this stuff. So this model says that you're going to prefer customer paths over peer paths over provider paths. So let me explain what that means. In interdomain routing, there are different types of business relationships. So this is a classic business relationship. What you have here is two very large networks. They're called Tier 1 networks, okay? And these are networks that have global reach. They're not localized inside one country. So this is like not the Pakistan telecoms of the world, which serve Pakistan, right? This is international networks that do transit across the world. Now, these two networks are considered to have roughly the same amount of traffic that one is sending to the other. So they're equally sending the same amounts of traffic to each other. And this is the agreement between them is what's called a settlement-free peering agreement, which means in order to send traffic for level 3 to Cogent or Cogent to level 3, nobody pays anyone anything. Okay, so this is sort of free peering. Okay, so no money changes hands. The reason for this is because these are equally sized networks, equal sized networks. Okay, so now the other really classic relationship is called a customer to provider network. So this is BU. BU is a customer of level 3. We are a small dinky network that serves only one, place. Our campus in Boston, our 2 campuses in Boston, that's it. We have very many providers actually, but some of our providers are level 3 and Cogent. And all that we are doing is, we are not a node in the internet. We're kind of like what's called a stub. We're at the edge of the network. We send traffic and receive traffic, but we don't carry traffic for people. Okay, so this is a small network. It's a customer network. Now, when I show money flowing this way, sometimes people see this money flowing this way and they think, okay, if I'm sending, then I have to pay, but if I'm receiving, do I have to pay? What's important to remember here is that both for sending and for receiving, I have to pay. Because I'm small and dinky, I don't provide service, I just use service, I'm a consumer. Okay, so money is going to flow from BU to level 3, either for sending or receiving traffic in both directions. Okay, so does that make sense here? Okay, so the Gao-Rexford model says that if I am a network and I have a route to somewhere, and that route goes through a customer, I should choose that route. Why? Because the customer pays me. So if I choose that route, I'm going to make money. Okay, so that's what the Gao-Rexford model says. So for example, let's say level 3 had a path to BU's IP addresses directly through BU or through Cogent. So this edge is free. He doesn't have to pay anything. But if he uses this one, he gets paid. Okay, so naturally he's going to choose this path because it makes him money. Okay, that's what it means to prefer a customer path. Okay, if, for example, there was a case where he had a route through, let's say, a peer where he doesn't have to pay versus a provider, so someone he would have to pay, I haven't shown that in this picture, he's going to choose the peer route. Okay, so this Gao-Rexford model is basically it's assuming that routing decisions are made just on who the neighbor is that's giving you the route, and whether or not you're paying him, not paying him, or getting paid by him. Okay? Does that make sense? All right. Okay, and then subsequently to this, there's, prefer the shortest path, and then there's other things that I'm not going to model in this talk. These other things, in case you're interested, they have to do with like the actual point where you're connected. So if I'm an autonomous system and I have routers in different places in the world, I may prefer the router, that goes to London versus the router that goes to Amsterdam. And that sort of stuff happens in BGP as well, but I'm not going to model any of that in this talk. Okay. So, there's also something important here, which is an export policy, and this is going to lead me to another attack that I'm going to show you. So, part of the Gao-Rexford model is this export policy, which says I'm going to announce a BGP route to a neighbor only if the neighbor is a customer or if the path is a customer path. So I'll show you what this means in a second. So, before you were probably thinking that every time I get a BGP message, I tell all my neighbors about the route I selected, right? And then they decide whether or not they want to route to me. Okay? No, that is not what you do. You only tell the neighbors that you want to tell. If you told everyone, they may all route through you, and you don't necessarily want people to route through you. For example, if I'm BU, I don't want level 3 to be sending traffic to Google through my network. right? That would be bad. I'm not engineered to carry traffic like this. So for example, we don't want this sort of routing, right? We don't want traffic from Cogent to go through BU and then out to level 3, right? That would be horrible because this would be a massive traffic that we would have to carry. Now notice that from Cogent's perspective, this is awesome because he's getting money from BU. So his routing policy would actually, if he had this route or this route, he would prefer this one because it's the customer route. Does that make sense? Money is coming from BU. But BU now is not going to be very happy because it's carrying traffic from one tier 1 to another tier 1, 2 huge networks using it for transit. That's not what BU is designed to do. It's just a network for a university. Okay, so there's this export policy that says, I'm only going to carry traffic for other people if either the route is through a customer, so I'm getting paid from the person I'm sending the traffic to, or the person I'm announcing to is a customer, which means the person who is going to send traffic to me is my customer. So something like this would only happen if one of these links was to a customer. In this particular case, both of them are not to customers, and so this won't happen. Okay? Yes? No, actually, not announcing is enough, because not announcing means that the guy never learns that you have that route. Okay, yeah, that's true. So Cogent wouldn't go manually introducing routes to BU under normal conditions. Like, even though they would make more money if they did that, they'd take BU down, and all of their traffic would go down because BU would collapse, and that would be really bad for them. It would be a very bad transit provider, and they'd probably lose customers. So under normal conditions, you wouldn't go install static routes that do this crazy thing. This is the kind of thing that happens by mistake, actually. These are the kind of things that happen either as part of routing attacks or misconfigurations that lead to it. Yeah, so I don't know of any cases that this has happened maliciously, but this example here, if BU was to screw up and to announce, let's say, the level 3 route to Cogent, that would be called a route leak. It's basically you're leaking a BGP announcement to someone you shouldn't be leaking it to. That's the sort of technical term for this sort of thing is a route leak. And it comes from this assumption that you're really only going to carry traffic from someone if they're paying you to do it. Okay, so I'm only going to be sending it out on this path if my neighbor that's going to route through me is my customer, or if the person I'm sending it to here is a customer. Someone's paying me and making money somehow. Okay, does that make sense? Okay, so this is a route leak. Here you go. So this is an example of a route leak. Here's our poor prefix over here that we've been attacking over and over again. Okay, so if BU here decided to claim, sorry, this should say /24. That's a bug in my slides. So if BU was to claim that they were the origin for this prefix, the one that belongs over there, what would actually happen here? So if you remember, okay, so this is not a good animation, but basically what would happen here is that, okay, so I apologize, this slide is completely wrong. Let me tell you what I wanted to say. Okay, so what should happen here is that BU knows how to get to this prefix. The route that it uses is level 3, 5034, 2997. Okay, so this is the route that BU would have, and it could select this route, and that would be very nice and fine. Okay, now what could happen though is BU could decide to announce this route to Cogent, right? Which could have learned this route itself. Right? But also it could have learned it to BU. Now which path is more successful? This path makes more money, and this path is which makes money. Okay, and so in that case, if BU was to mistakenly announce and if this happened for a lot of prefixes, BU would collapse. Okay, so when I showed you that in this attack, that was exactly what happened. They leaked routes, so they started announcing routes to neighbors that they knew. So that's a route leak. Make sense? Okay, so the classic route leak is you announce the route you're actually using, but just to someone you shouldn't really be announcing it to. And then because you're preferred, because you're a customer, the traffic will go through you. Okay, so that's a route leak. Now, in the late 90s, when these attacks started happening by mistake, and I always say attacks, so please forgive me, I don't always mean that they were maliciously done. I've tried to make the distinction that they were, I used to say that we'd never know that they were maliciously done, and now I would say from 2013 onwards, we know some are maliciously done and some are mistakes. So when this stuff happened and they started to think, how are we going to fix this problem? What they developed was prefix filtering. So for people who are, in security, I've shown you like a crypto protocol, I've shown you a certificate protocol. This is an access control protocol, okay? So what it's saying is it's just you're going to have access control lists. This provider is going to keep a list of the prefixes held by BU. Okay, now, how do you know what prefixes are held by BU? BU is a stub. It only is supposed to be, it's only got providers. So a stub is an AS that has no customers of its own. It doesn't have any customers, it just has providers. So by what I told you before, if I have no customers of my own, nobody should be routing through me. I should only get traffic and send traffic. I should either be a source or a sink. I'm not a node, I'm just a source or a sink. That's what a stub means. Okay? So for stub networks, you know exactly what BGP announcements you're going to see from those networks. You're going to see them for the prefixes that are actually owned by those networks. Does that make sense? You will not see any routing announcements for this networks unless it's prefixes that are actually belonging to this network. Okay? So what you need to do is just keep a list of the prefixes that belong to this network. And then when you see anything that doesn't match this list, you drop it. That's it. Access control list. Okay? So in this case, level 3 knows the prefixes that are held by BU. It sees the BU is announcing a prefix that it doesn't have, and level 3 will just drop it. Similarly here, the Cogent could have a prefix list of the prefixes owned by BU and then just drop the prefixes, drop an announcement if it doesn't match the prefix list. So we've had this technology for a long time, actually. We've had this for like 20 years. And this is actually done today. And so when I told you about the Pakistan YouTube incident, one of the reasons that actually hit the whole internet was because the provider of Pakistan Telecom was not doing prefix filtering properly. For Pakistan Telecom, it didn't catch the fact that Pakistan was announcing something completely unusual, and it passed it on. Okay, so it's the equivalent of this type of incident where like BU was announcing some nonsense and his neighbors were just letting him. Okay, so prefix filtering is done by a lot of networks, but not done by all networks. So we can't always assume that it's there, but if it was there, we would be doing pretty well. Yeah. Good question. So very little in the sense that like he doesn't really gain anything. He's protecting the rest of the internet from the attacks, from attacks by its customers. So prefix filtering is like an altruistic technology. If you do it, you protect your neighbors from attacks by your customers. Okay? But then you are really, really embarrassed when you like your entire network goes down because you did something so stupid like send all of Google's traffic through Malaysia Telecom, right? So there's also an issue, like a big driving factor in internet security is not doing stupid things and being shamed in front of your fellow operators. So I think the operator community is very, very well connected, more than you'd expect. So the operators of all these networks know each other personally. They go to Nanog every year. They meet each other. It's a really close community. So being the person who let Pakistan Telecom hijack YouTube, it's not a fun thing to be. Like, you don't want to be known for that. So it's actually a very good community. They work together a lot, and they will like phone each other in the middle of the night and like help each other fix things. It's a very altruistic community actually, and that's part of the reason that a lot of the system stands. Yeah. Transit. Yeah. Yeah, so that's why we have networks like level 3. I mean, level 3's business model is that, one of its business models is that, you should choose the path through me because I'm better connected. Right? So what I'm saying here is, you said you want to make money, right? So I'm saying that the only reason that you would ever announce anything to anyone is if you're making money. So when do you make money? when someone's paying you. So what I'm saying is, as long as one of the links is paying you, either one, either the in or the, either this one or this one, then you're happy to announce. But if no one's paying you, then why should you announce? Oh, I see. So you're saying globally, like through doing a package of multiple prefixes and stuff like this. Yeah. Yeah. Yes. Yeah. Yeah. Oh, sure. Yeah. I mean, that's definitely allowed. That's allowed. I mean, look at it. I've shown you here in this picture, right? So you're seeing end layer announcing a path to this prefix that's held over here, right? So yeah, you can definitely announce to prefixes that you don't hold. I'm just saying that you're not going to start announcing things to people unless one of the sides that's using you for transit is paying you. Yeah. Yeah. That's true. That's true. Right. So making money in other ways, there's two important things about that point. So first of all, yeah. So when I showed you a route leak, that's exactly if you are a hijacker and you want to do stuff, you'll certainly break this sort of rule of thumb, right? A lot of networks also, like Google's links with most people and with most other networks are settlement-free peering agreements. The reason is because they really don't care how much it costs them to route traffic. That's not their business. Their business is to get you on their websites. So they will peer with everyone. But the thing is that the policies that are still used by everyone, it's just that the link is just a peering link. Okay, so typically what tends to happen is that Google is not a service provider for the internet at large. It's a service provider for its own services, right? So you don't go through Google's autonomous system in order to reach a Microsoft website. You go through Google's autonomous system to reach a Google website. So again, Google is actually kind of acting like a stub. It's a source and a sink for traffic, as I said, even though it's huge. And it's very, very well connected, actually. So what we call these types of networks are content provider networks. Those are networks that make money by doing something else, generally providing content. They have no problem peering with tons and tons of networks. But again, they're not acting as a conduit for traffic between two other networks. They're serving their own services to the world. Okay. Yeah. Sure. Yeah, you could. You could. So for example, you could do surveillance on the traffic, and you could be a country that has lots of international networks, and you could have lots of connections and want people to go through your network, and now you have a lot of traffic to look at. So certainly you could do that. Yeah. More questions? Okay. All right. Okay. So this is the thing that we have now, prefix filtering, and now I'm going to actually show you some results. So that was the background. I want to start by kind of looking at, we have 3 different solutions that we've looked at. We have RPKI, BGP Sec, and prefix filtering. Okay, so we want to see the impact of these technologies on attacks. So what we did was we had to do simulations because you can't attack the internet and see what happens. You have to test somehow. So what we did was we had a graph of what the internet's autonomous system level graph looks like. We ran tests on that. This is a 2012 graph. It's a little old paper. What we did was we randomly selected attackers and victims, and we tried to see how traffic would go under the assumption that the routing policies used were the ones I showed you in the Gower-Rexford model. Okay. I should say that not all routing policies follow Gower-Rexford. Most of them do, but we don't know what routing policies people use because they're personal, they're local policies. I don't know what every network does, so we use the Gower-Rexford model to get an idea of what's happening. So what I'm going to show you is an estimate of how things work, not like the answer of how things would really happen in the actual internet, because I don't know how routing policies look like at every network. Okay, so what we do here is we evaluate these 3 technologies, and what we're doing is we're evaluating the impact of the attack that succeeds against each technology. So let's start with this thing here. Okay, so this is the world in which there's nobody's doing prefix filtering, and this is the world in which everyone is doing prefix filtering. Okay, what is the best attack you can do against BGP? it's a sub-prefix hijack. As I told you before, if you do a sub-prefix hijack, you hijack everybody, right? Not just the people close to you, everybody, if your sub-prefix gets out into the world. So if we're like evaluating the impact of sub-prefix hijacks, this is what happens if nobody does prefix filtering. So basically, most of the internet would actually fall for the attack. So this is the average fraction of networks that select the route through the attacker. That don't select the route through the attacker. Okay, so if nobody's using prefix filtering, most people are not going through the attacker. They're reaching their real destination, and they're Okay, if most people are doing prefix filtering, if everybody's doing prefix filtering, 85% of ASs will not be attacked. Okay, if prefix filtering was used throughout the whole internet. If nobody uses prefix filtering and we have sub-prefix hijacks, then the majority of almost 100% of traffic will go to the attacker. Okay, so let me say that again because I was having trouble speaking. We want to look at the world in which there's only BGP. What's the worst attack you can do against BGP? Sub-prefix hijack, right? Because that works regardless of your position in the network. Okay, so if we do a lot of tests of sub-prefix hijacks, okay, choosing random attacker and victim, and we see what fraction of networks actually go to the attacker. When BGP is used, almost 100% of the traffic goes to the attacker. When prefix filtering is used, only 85% of traffic goes to the attacker. Why is that the case? It's the case because the majority of networks are actually stubs on the internet. So if you were able to prevent all of these stub networks, just the sources and the sinks of traffic, from doing stupid things, then most attacks are stopped. Okay, so that's what I'm showing here first. So there's a huge gain of going from no prefix filtering to prefix filtering. Okay, let's look over here. This line here. This is BGP Sec. This is the world in which we have BGP Sec. Everybody's deploying BGP Sec. What attacks can you do against BGP Sec? Basically not very much. The only thing you can really do against BGP Sec is kind of like, you remember how I showed you a route leak? You're announcing routes to more people than you should. You can't lie about the route itself because it's all signed, but you can send it to more people than you should. Okay? So basically, when you have only the power to send real routes to just a little bit more people, you can hijack a little bit of traffic, right? So like 5% or something. But you can't, most of the traffic is going to be unaffected by your attack because really you're announcing real routes, but just to more people. So these route leaks are very, very limited in impact. Okay? This is the world in which people do both BGP Sec and prefix filtering. You can do them both, right? They're parallel technologies. BGP Sec ensures that the paths you announce are actually the right paths. Prefix filtering makes sure that stubs don't announce any routes that are not theirs. So route leaks by stubs are stopped. You can see that basically you have like 2% of ASs are impacted by attacks. We've solved all our problems. Okay, so this is the perfect world. Yep. So if you're not a stub, so let's say you're Cogent, and you're announcing paths to more people than you should. Actually, Cogent is a bad example because it doesn't have providers. Pakistan Telecom. Okay, Pakistan Telecom is not a stub. It provides services to lots of other networks. So in the world of BGP Sec and prefix filtering, Pakistan Telecom could announce real routes that it really has to too many people, and then some extra traffic will go through them. That's pretty much it. Okay, so that's this tiny little sliver over here. All right. Ignore this, because I'm not talking about this. This is the RPKI world now. So if we have RPKI, what is the attack that succeeds against RPKI? It's the thing you pointed out. It's the case in which you can no longer do sub-prefix hijacks. You can just announce the right prefix with the right first hop, and then claim that you're next to them. Okay, so this is the world in which you just have the RPKI. And you can see, actually, that a large amount of traffic is protected. So like 70% of traffic is fine, and 30% of traffic will be attacked. Okay, so just want to call your attention to, this is the RPKI world and this is the BGP Sec world. So you see the difference isn't huge. Okay, so one thing that's important to note is while BGP Sec does bring a big performance security improvement, it's not a huge difference when you go from RPKI to BGP Sec, but there is a huge difference when you go from RPKI to nothing, to no security. Okay, and the reason for this is because sub-prefix hijacks are horrible. They're really, really effective. Yep. Yes. Yeah. No, you're right. No, you're right. You're right. So, I mean, one thing you could say is all of this stuff is bogus because you are really worried about very targeted attacks on specific DSs. And in that case, yes, 100% you need full BGP Sec deployments. But what we're trying to measure here is like, okay, so first of all, your question of like a particular attack, like what could happen to a particular network, I could simulate that, but I can't present that in a meaningful way, which is why I'm presenting it in this way. If you were to actually want to protect every single network from attack all the time, you would really need to use BGP Sec with prefix filtering. What we're trying to show here is what is the sort of scope of an attack? How far does it propagate? And that's what these numbers are showing you. The propagation of the attacks that succeed against these protocols is much, much lower than the ones that succeed against insecure BGP. Yep. Yep. I am talking about AS pairs. So, yeah. So for a given, so a randomly chosen attacker and victim, how much traffic would actually go to the attacker? So I have the victim, I have the attacker. How does traffic split? So what these numbers really show you is the split of traffic. So in the case where you have no security at all, random attacker, random victim, all of the traffic goes to the attacker. Okay. In the case where you have BGP Sec, here, random attacker, random victim, most of the traffic goes to the legitimate victim. Yeah. Legitimate storage. Yes. Okay, so, yeah. Yeah, no, I understand. Okay, so, yes. We looked at, so it's really hard to quantify that, so the way we did it was we looked at different tiers of ASs. So tier 1s, how many of them go in one direction? Tier 2s, content providers. Turns out that in most part, actually, everything looks like this. It doesn't really look that different. If you look at our SIGCOMM 2011 paper, 2010 paper, there's a lot of figures that are looking at breakdowns of different classes of ASs. Actually, some of the figures we didn't even bother including because we always got this question. We did a lot of simulations for different tiers, and they almost always look the same. So, you know, I think the right way to think about this is like, what is the impact of these attacks? When people see RPKI and they say, oh my God, but there's still this attack, the point that we're trying to make is, yes, there's still the attack, but the impact of the attack, the number of ASs affected by the attack is growing smaller and smaller. Okay? And then I think what I want to point out here is that, you know, the number of ASs that can be affected by an attack where you have sub-prefix hijacking versus the number where you have that one hop hijack, right, where you have to be claiming to be connected to a legitimate destination, much, much fewer can be attracted. And even when you compare from here to here, you don't see the huge jump that you see from here to here. Okay, so BGP Sec is giving you a marginal gain over RPKI in terms of limiting the scope of the attack. That's how I like to think about it. And what I think is really interesting about these results is that if you combine RPKI with prefix filtering, you actually are doing almost the same as you would be with BGP Sec. And remember that these two technologies, RPKI and prefix filtering, are not changing the BGP message structure. They are access control technologies. Okay. Yeah. Yes. But I'm assuming, yeah, exactly. And I'm assuming that everybody does prefix filtering and everybody is well behaved, which is not a good assumption because that's not true. But this is just to show you sort of the scope of these attacks, so yeah. So yes, it's true that sub-prefix hijacking actually does better than RPKI, right? When you combine the two, you start to get these big improvements. Okay. Yes. No. Yeah, I know. There's something very disturbing about hearing someone in security talking about randomly selected attackers. I agree with you. I mean, it's frustrating to me. I have to sort of admit that, like, we needed to find a way to quantify this. It had not been quantified prior to this work. We were trying to think, like, how do you actually argue about this? And so the way I like to think about it is really in terms of scope of attack. Okay, so this is what I'm capturing here. I'm telling you, if you make an announcement, how many people are you going to affect? And so if you want to think about this from the perspective of, like, we want to stop all attacks all the time, then you need to go all the way to BGP Sec with prefix filtering. By the way, you know, it's not necessarily obvious if you think about it that you should think like, oh, if I had BGP Sec, I don't need prefix filtering anymore. No, I'm telling you, you still need it, okay? because these attacks, these route leaks, where you announce more broadly than you should, they're still effective. You can see there's an improvement here, right? And that was actually not clear before we wrote this paper. I think it's totally obvious now if you think about it, but that wasn't obvious at the time. So I'm telling you need both. And I'm telling you that the scope of the attack gets smaller depending on the technology that you use. Now, I can't tell you about it. I mean, I could write the simulation for you, but that's not, like, how do I present these results to you? Yeah. I could. I don't know. I still see a big jump here, right? It's a big jump even if I flipped it, and this jump is small. Yeah. No, it is actually. That's okay. Okay, okay, that's fine. I accept that. I will show you some more stuff about BGP Sec shortly that will turn some of this around. We're going to take a break, right? Yeah. So just the final thing that I would say here is that we saw the protocols, we saw the attacks they allow, and it's true that each protocol stops different types of attacks and progressively less damaging attacks, actually. And that's what I'm trying to show you here. So the very first solution that you put in here kind of kills the really horrible attacks, and then you get these less horrible attacks that are still there. Okay, so then we'll talk more about partial deployment after that. After this. Okay, so. To ahem. All right, so I want to go on to look at a very specific study we did now. We saw now that RPKI, we saw the impact of prefix filtering in RPKI and BGP Sec. Okay, so all this time I've been talking about the difficulty of upgrading to BGP Sec because it requires a change to the BGP protocol. And so what I want to do now is I want to consider BGP security and partial deployment. So I was just talking to someone who works at the .il registry who's currently deploying DNSSEC. So DNSSEC is a great example of a secure protocol that's been in deployment for a very long time. And you'll note that the Israeli TLD has only done the deployment, I guess, a month ago, right? So these protocols take a long time to roll out. And so what we want to study in this part of the talk that I hope will be short is what happens during this period in which BGP Sec is being deployed, where some networks are deploying it and others are not. So today we're living in a world where nobody deploys BGP Sec, but we wanted to understand what would happen as the deployment proceeds. Okay, so the reason we want to see this is because this deployment we believe will take a long time, so we want to see what sort of security protocols properties we can get from this. Okay, so what we're going to do now is we're going to try to understand. This is from a paper that we called "Is the Juice Worth the Squeeze?" BGP Sec and Partial Deployment from SIGCOMM 2013. And what we were studying was in this period where you go from just having the RPKI to having a BGP Sec deployment, what sort of benefits do you get? Okay, so we want to see the marginal benefits of BGP Sec over RPKI. So the way we choose to evaluate this in this paper is to assume that RPKI is deployed by everyone. Okay, prefix filtering is deployed by everyone. So that means that we're in this curve here. Here, okay? And we want to see what additional benefits we get from moving towards a BGP Sec deployment over here. Okay, so you can kind of look at these lines and kind of guess where I'm going with this. But I want to point out that the results I show you are pretty much generalizable to the case where you don't have prefix filtering. So it's really just, we're measuring the difference between RPKI and BGP Sec. Okay, and I'll show you exactly what I mean by that as I go on. Okay, so we want to understand what is the marginal benefits of BGP Sec? Okay, so in order to do this, what we're going to look at is what happens in the world of BGP Sec in partial deployment, where some networks deploy BGP Sec and others don't. So this is now we're going to get into this backwards compatibility issue. Okay, so here's our BGP Sec announcement that green host gets. You can see that there are 4 different signatures on this: the blue, the red, the green, and the yellow. That's here, this thing. And we need to think about what happens in a world where BGP Sec is not deployed in some of the networks, okay? So in a world where some networks deploy BGP Sec and others don't, I'm going to be getting BGP Sec packets and BGP packets, secure packets and insecure packets, messages that are signed and messages that are not, okay? So now, I could be very, very strict about this and say I will not accept anything but BGP Sec, but that's going to be horrible because if the whole internet doesn't deploy BGP Sec, I will lose connectivity to the internet. So you naturally have to accept both. Okay. So now the fact that you naturally have to accept both for functionality is going to also be an attack vector. So people who work in this area, you've probably heard the term downgrade attacks. So here you go. This is a downgrade vector. So we're going to look at a lot of these sort of attacks that are essentially downgrade attacks from BGP Sec that exist because you need to be able to support BGP Sec alongside BGP if you want the internet to work. So that's a sort of non-negotiable requirement. You can't have BGP Sec and just turn off BGP just like that because you will not have deployment at the same second by everyone. Okay, so in this world where some people speak BGP and others don't, you are going to have to accept both types of messages. So we can find ourselves in this case again, where this guy, Cyberbunker, will send a plain old BGP announcement that's been downgraded to BGP, or maybe he never deployed BGP Sec. And this is an announcement that would have worked. You know, we have RPKI, so this is going to pass the RPKI test, right? You can see that this autonomous system and prefix match these autonomous system and prefix, right? But it's not going to be a valid path because he's downgraded to BGP, so he doesn't have to give you valid paths. Okay? All right. So now we have a choice. It comes down to this network over here, and he's got a choice. He's got this RPKI valid announcement that's not told to him with BGP Sec, and he has an announcement that is told to him with BGP Sec. What should he do? Choose BGP Sec, obviously, right? Because it's a cybersecurity school. And so if he did that, we would be all fine. Okay? But actually, that's not necessarily what's going to happen. Okay? So what we did was we started this research by trying to understand what sort of routing policies people would use in a world in which BGP Sec is partially deployed, where you have to accept both BGP and BGP Sec. Okay? And there's a lot of stuff in this paper. I'm not going to get into all of it. But, you know, there is actually something to think about here, because if you look at this case, this guy has a 4-hop route that's BGP Sec secure, and he has a 2-hop route that's BGP secure. You could also imagine a case where he gets a BGP Sec secure route through a provider where he has to pay, and the path is really long, versus an insecure route through a customer that's cheaper and he doesn't have to pay. So what is he going to do? Okay, so again, the specs say this is a matter of local policy. Okay, how are you going to make your routing decisions as a matter of local policy? And so what we did was we tried to understand how the system would behave with different local policies. Okay, so we had this thing that we called security first, which is that you would prefer secure routes over everything else always, and we evaluate security with this. We had a different model where we assumed that people would do local preference before security, so that means that they would look at the cost of the route before they looked at whether or not it was secure. And then we had this third model that was security third, which is that you would put the length of the route as a priority above the security of the route. So we studied all of these. We actually asked operators what they would do, and we got 100 responses from operators through a survey. So 41% would select this in partial deployment because they don't want this to affect their routing very much. Okay. So you can think about, in the paper we talk a lot about this, like if you were to partially deploy BGP Sec, there are scenarios in which you were previously using customer routes or short routes, and all of a sudden you're going through providers all the way around through these long routes. And these things can also have not only a performance impact, but a security impact, which I can talk about offline later. But anyway, we have these 3 models, and we're going to consider how the system behaves in all these models. Yeah. That would, no. So I don't know, that application layer decisions in BGP I don't think happen very often. Maybe you could have a by prefix level decisions. So you could say for prefixes that belong to banks, then you could do certain things. I don't think it would happen by application. The decisions are made by prefix. But you could say, yeah, these are important prefixes, do things like this. And there are actually prefix level policies. Again, this is all theoretical now because nothing is deployed. So you could imagine having prefix level policies. In this analysis, because there's so many different factors to untangle here, I'm going to assume that everybody does the same thing. So one policy, the other policy, the other policy. We actually showed that really weird stuff can happen if people mix the policies, but that's a different thing. Okay, so let me try to look at our question here. So if everyone uses the same security model, so I know that people will not all use the same security model, by the way, the survey kind of points that out. But we needed somehow to model this thing, otherwise it gets out of control. So if everyone uses the same security model, what are the benefits of deploying BGP Sec at some set S of ASs? So just so you see the kind of parameters we have here, and to me this research problem was very daunting. It's something that I wanted to do for a long time. And the reason this is so daunting is because you have to decide how the routing policies are, and you have to decide who deploys. Okay, and you can imagine any subset of ASs deploying, and then you have to evaluate all of these things, and it starts to get out of hand. So I'm going to simplify this all down for us, okay? And this was the cool thing that we did in order to write this paper, to be able to simplify this. So the first assumption I'm going to have to make is that everyone uses the same security model, which is an unfortunate assumption, but otherwise I can't really do anything. So let's just assume that and see what happens. Okay, and now what I'm going to do is I'm going to get rid of this parameter, the set S. Okay, I'm going to somehow magically get rid of it. Let me show you how. Okay, so this is a protocol downgrade attack in which you can see these slides are old. Okay, so this is a protocol downgrade attack. So what happens here is that if you have a guy who puts security lower in priority than route length, what he's going to do is select this route through the attacker. Okay, that's what we call the security third model. Okay, so you could say to yourself, if this guy is stupid enough to prefer shorter routes over secure routes, he's going to get attacked, and you would be right. Okay, that's true. He will get attacked. If he prefers shorter routes over secure routes, he will get attacked. But I want to point out to you something here, is that this guy here, Greenhost, getting attacked in the security third model, he's always going to be attacked. It doesn't matter who's deployed BGP Sec. Okay, so for example, let's imagine that everybody has deployed BGP Sec except for the attacker, right? In this case, the attacker will still choose the route through Cyberbunker because it's shorter. He doesn't care that it's not secure. Now, if nobody's deployed BGP Sec, what is Greenhost going to do? Still, he's going to choose the route through the attacker because it's shorter. It doesn't matter. It doesn't matter who's deployed BGP Sec. Let's look on the other hand, and whatever, pick any set of networks to secure. It doesn't change the decision of Greenhost. He's always going to pick the shorter route. It doesn't matter if BGP Sec is there or not, because route length is always going to be more important to him, and the attacker's route is shorter. Done. Okay. Now if we look at these guys, so we call him doomed. Now if we look at these guys, if nobody's deployed BGP Sec, what routing decision is this guy going to make? He's still going to go on the legitimate route because he's closer. So the attack has no impact on him. Okay, so these two networks here are always going to choose the legitimate route because it's closer. So we call those networks immune. Okay, so the deployment of BGP Sec for these networks has absolutely no impact either. Right? If they were all secure, great. Doesn't matter. They would still be fine even if they weren't. Right? And so what I'm getting at here is in this particular, contrived graph that I chose for you, there's only one network here where it matters who's deployed BGP Sec or not. And this guy here who has the choice of like this 3-layer real secure nice route, and this guy who has a 3-hop bogus route. Okay, and this is the guy for whom BGP Sec is making the difference. So in the security third model, only a very, very limited number of ASs are actually going to be affected and change their routing decisions based on it. Yeah. Yes. Yeah, because so I told you that we had 3 models for routing security, how they would incorporate this in their routing policies. So in some sense, I've been focusing right now on the stupidest one, in which you always prefer the shortest routes. But by the way, this is the one that was most popular. Okay. Why? But, you know, it sounds kind of like, why would you do this? But this actually makes sense, right? You're an operator. You're testing a new technology. You're not going to all of a sudden, like, accept these huge swings in your routes during the partial deployment phase. You're going to want to make sure that paths are still sort of short and performant before you kind of make dramatic changes because of BGP Sec, right? So this is the kind of conservative from a performance and operational perspective policy. And I'm showing you the impact it has on the actual security in the case of attacks. So remember, attacks are not the common case, right? So if you're optimizing for the common case and you're sort of the uncommon case, then this is what happens. Yep. Yeah, maybe. Could be. We first need to deploy it a little bit, though, which we haven't done yet. But anyway, I just wanted to point out that, you know, these policies, depending on the policy you use, some networks, the deployment, like the set of deploying ASs, the wideness of the deployment has no impact on you because of your position relative to the attacker and the victim. Okay, that's the point that I'm trying to make here. So naturally, if, you know, we use the policy in which security is the highest priority, right? Actually, you know, all of these guys will prefer to take this route, regardless of the fact that this is shorter. So this attack will fail. So there's going to be a lot more networks that are affected by BGP Sec in the security first model, right? But in the security third model, a lot of networks are going to be immune, like these ones.